going to record this on my computer. Okay, so let's start again. Okay, so System View is a software which is used for system simulation. It provides interface to MATLAB, communication block set. It provides you interface to VHDL. It has an interface to Xilinx Vivado, right? So if you have something implemented for Xilinx FPGAs in VHDL or Verilog or System C, you can take it to System View, and you would be able to do radar and communication systems in System View. So System View basically came from two places. One was Eagleware System View. Other was your GUI was borrowed from Genesis, right? And then the Ptolemy engine was put from ADS, right? And then there were lots of things added, like interface to MATLAB, to VHDL, Verilog, and that made System View. So if you know Genesis, you know everything in System View, where to find what. So that's System View. Now, can we do the entire stuff in ADS? Of course, yes, because Ptolemy is a part of ADS, right? So whatever you can do in System View, you can do in ADS. But then here they have automated a lot of stuff. They have made template kind of stuff. So like, for example, they call it virtual test bench. Okay, so that is VTB. So you have to buy a separate license for VTB to do various communication systems like 4G, 5G, and all that. But nothing stops you from doing this in ADS without a license. You can buy VTB for ADS, virtual test bench, to test your stuff. So that makes easier. But what I will show you is that you don't need a VTB. You can do your EVM, ACPR, everything, because everything is in there, right? So that's there. Now coming to Genesis. Okay, again, Genesis was earlier some other product which they acquired. They build it up, and Genesis has a different interface, not like ADS, which is a multiple document window, or MDF, what they call MDF, multiple document files. While it is it has a MDF, but it doesn't have multiple windows, right? So for example, this window or that window, everything sits inside one GUI. That's a different GUI. That GUI they tried for ADS, but then people didn't like it. So they went back to what ADS was, right? So what Genesis can do. Okay, like for example, here in ADS, they have something called harmonic balance, right? Which is a Volterra series techniques. Okay, what is a Volterra series technique? Very easily, okay. There is, whenever there is a system, it has a transfer function, and your signal is convolved with the transfer function to get the output. Now, very simply put, you can always interchange signal and transfer function, because it's just a convolution between two signals, right? That means that a system transfer function is nothing but a second signal, right? So you are performing convolution between two signals, right? So that means that if there is a nonlinear system, okay, a nonlinear system can be broken up into like sinusoids, just like your Tyler or your Fourier series expansion. Any nonlinear waveform can be represented as a summation of linear waveforms, right? Same thing is over here. A transfer function is nonlinear, but then you can, if it is equivalent to a signal, you should be able to split it up into a weighted sum of sinusoids, right? And then you can solve the circuits for each sinusoid. And then because for each sinusoid, the system is going to be linear, right? Because there's nothing nonlinear once you have done a Fourier expansion or a Tyler series expansion. Okay, there is nothing called nonlinear. Everything is a summation of linear sinusoids. So now a nonlinear system can be split up into linear systems at different frequencies, right? Fundamental and harmonics. And you can solve the circuit for that. And then the principle of superposition will still apply. And you should be able to construct back your waveform from a nonlinear system, right? So that's the thing which harmonic balance or Volterra series is. Now, this whole harmonic balance thing has a restriction. Okay, restriction is that if there are multiple RF paths, okay, then harmonic balance cannot handle it, or envelope cannot handle it. So this limitation you should know of harmonic balance, whether the harmonic balance is in cadence or whether the harmonic balance is in ADS. It's inside a Volterra series technique. There is a limitation on number of paths you can simulate in harmonic balance, right? So that's your restriction. So now when you design a transceiver, for example, there are leakage paths, right? I think somebody dropped out. Let me admit. Okay, so there are leakage paths. There are multiple RF paths, right? So harmonic balance is not for that. Harmonic balance assumes that there is a single RF path, okay? Or rather, even if there is a feedback, you cannot show as a third terminal. There has to be a one input terminal, one output terminal. There may be feedbacks in there. That's okay, but it'll simulate only one RF path. Okay, it cannot have multiple RF paths. Now, this was a major limitation in transceivers. Okay, this was solved by something called SPARCA. Okay, a SPARCA technique basically allows you multiple RF paths. Okay, so if you use Spectrasys, it is based on SPARCA, and Spectrasys, which is available in System View, which is available in Genesis, allows you multiple RF paths. So you can see component at any node coming from different RF paths, and it will notify where they are coming from, right? This is not what you can do in harmonic balance. So when you do transceiver designs on, let's say, system level in System View, or let's say in system level in Spectrasys, you would be using a different technique, and that would allow you to evaluate leakages, reverse paths, right? Stuff like that. So for transceivers, the best suitable software would be Genesis, because it has Spectrasys, not harmonic balance. Okay, so harmonic balance is there, but it is used in a limited sense. So Genesis also allows you to do circuits, which System View doesn't. So basically, you can have a PDK in Genesis. Now, people will say there are no PDKs for Genesis. Well, you know, when somebody says that, I can develop my own. For example, the PDK I'm going to use, that was developed initially as a Silterra PDK, and later it was, you know, accommodated into this PDK, right? So once you start using software, the limitations which, you know, the software guys will tell you that this is the limitation. That's not the limitation, actually. That's just that you have to do too much work. And if you are ready to do too much work, then there is nothing stopping you. So in Genesis also, you can have a PDK, and you would be able to design circuits and use this with system simulation in Spectrasys. I have done this in Macris around 10 years back, PDK. That was in Malaysia Remote Sensing Agency. Okay, so that is there. So Genesis will allow you to do transceiver analysis and design. So that's basically three. Now the fourth software, which is called EM Pro. Okay, now what is EM Pro? Earlier, there was a company called XFDTD. They had a simulator, which is a finite difference time domain method simulator. Okay, they borrowed it from University of Utah, where I used to work with the lady professor, Cynthia first, and then there was one more gentleman, Om Gandhi, and they borrowed it from Susan Hagnes and Alan Teflau, right? So those people were the people who wrote this code, and they handed it over to University of Utah, and University of Utah basically, I think, sold or handed over to XFDTD, or it was a spin-off from there, and then it was acquired by Agilent. And then they made a separate software where they put a FEM simulator along with the FDTD simulator and made a separate tool called EM Pro, right? And the thing is that the EM Pro GUI is much easier to use than HFSS. And if you get a chance to go through on EM trainings with me, I'll show you something which takes maybe hours in HFSS will take you less than 2 minutes in EM Pro. Okay, to enter the 3D design. This is because the way they constructed the GUI, or rather the CAD 3D entry, it's much more superior than what HFSS did. HFSS's own advantages. Okay, it has what you call high performance synthesis. Okay, HPS, for which you have to have a separate license. You can run it on multiple cores as a parallel simulation. Well, in EM Pro also you can do that, but then you might need a license. I have done simulation. I don't see that you need a license for doing a parallel simulation in EM Pro. So these 4 software tools are provided by Keysight. System View, you know what it is used for. Genesis, you know what it is used for. ADS, you know what it's used for. EM Pro, it's used for EM simulations, right? And EM Pro has connectivity with other tools. Now, what has happened, one more thing has happened in 2019, which has, rather in 2011, they used to have their own proprietary storage, okay, which was based on object linking and embedding. I'm not sure exactly if it was OLE or not, but some proprietary storage or database management was there. They started using XML, okay, or XML objects. Now I don't know if they use XML or JSON or whatever, but they started using XML in 2011, so that one tool can talk to other tool more easily. One tool can share the results with the other tool. So for that, they changed the database, the data set, how they store it in 2011. That's why ADS is not back compatible with 2005 ADS. All the PDKs which were there up to 2011, they cannot be used here in 2020, for example. This is because the storage or the data sets, that is entirely different. You can convert the projects from prior to 2011 to 2020, but you cannot convert back. So it is only one-way lane. You can take a project, convert it into 2020, but you cannot go back. So if you make modifications, you cannot run back in 2005. So it allows you to do that. Okay, let me admit. Okay, so that's the basic difference. Now let's compare this to Cadence. Okay, now a lot of people are used to Cadence. For that, what the Keysight or Agilent did was they introduced what is called RFDE. Okay, RFDE is more like a same kind of a GUI, or similar kind of stuff to give a same feel that you are using Cadence, right? This was more like marketing stuff. They also started what is called dynamic link. Okay, what it means is you can take a circuit in ADS, netlist it, take the netlist in Cadence through dynamic link and run it, right? Even the optimizers would work. So basically both are running on the same machine, Cadence and ADS, and they can talk to each other. They can exchange data, right? They can exchange netlist. So you would be able to use optimizers in ADS also, right? You can netlist in ADS, and then you can I think the other way is also there. You can netlist in Cadence, bring it in ADS and run simulators, because Cadence for a long time had been more like a transient simulator, PSS analysis and all that. Very late they added harmonic balance. Very late they added envelope, right? Very late they added EM simulation. I think they acquired the AWR for the EM simulations, right? So there are some limitations there. So for example, if you want to do HB analysis in Cadence, okay, only one tone with high power is allowed. You cannot put multiple high power tones. As far as I know, the limitation of HB in Cadence. Okay, so that's the problem. Same problem carries over to envelope, because envelope is nothing but time-stepped harmonic balance. Okay, so same problem continues with envelope. So it's restricted. Cadence implementation of HB and envelope is very restricted. Okay, in RF simulation, in nonlinear simulations, you need this kind of stuff. For nonlinear simulation in cadence, all you had was some kind of a transient simulation. And later on, they included these frequency domain techniques for communication systems and stuff like that. So cadence goes like that. There are other tools also which I don't use. For example, Microwave Studio or AWR, right? I tried it. I didn't like it. I discontinued it. So in this workshop, we'll be using ADS. So now let's see what is our timing. Okay, so this goes from 9:45 to 10:45. I have covered 4 tools, right? Now, I would like to give an introduction in ADS, but I'm assuming most of his stuff you would know, and you will be able to do that. But in between, let's open for questions, okay? Now, you can type in your question here if you have regarding these 4 simulators, right? Or, if you want to know limitations and stuff like that, or I'm going to unmute all of you and you can ask one by one a question if you have. So I guess I have unmuted all people, so they are free. I don't know. I think I have unmuted all the people. So if you have any specific question, you can ask me before we jump into introduction to ADS, right? So any questions you have at present? I think it's too early for questions. Once we start doing stuff, you will have questions, I think, right? So anyways, if you don't have a question, if some question pops up in your head, you just type here and I'll try to answer it. Okay, so let's go back to ADS. And instead of showing you a boring presentation, I would start working with it. Okay, presentations go only to a certain extent. Okay, so to launch it, ADS, you can launch from anywhere. You can launch from start menu. Okay, so for example, this one, you can launch from here. You might have an icon here, or you can add an icon here by saying right click and say pin to start. So it'll show up here, right? So this is ADS. Same thing with other tools also. So let me see if I have system view on this. Yeah, so you can launch system view from here itself, right? Or Genesis. Okay, I might not have license for these. Okay, so I'm not going to launch them. Okay, so what you can do is you can launch most of the Keysight softwares from Windows Start menu. You might have icon here, right? So for example, over here, so that's your icon. You can double click it to launch it. You can launch it from the menu over here if you have a button. You can put your button over here also. If you want, you can put your button here, right? So this is just like any other Windows software. Now, once you launch it, you see 2 windows here. Let me put this down. Okay, you see 2 windows here. Okay, so this is the child window. That's why it will not allow you to click on this one, because this is a child window, right? Unless you close the child window, the main window won't allow you. Okay, so this getting started window is where you do all your project management, right? A project is called a workspace. I think if I have a marker here, yeah. So this, okay, this shows recently used workspaces. So they are listed all over here. You can start a new workspace from here. And you can unarchive archive workspace from here. You can open an example from here, and your open workspace you can browse from here, right? So basically this window is good for project management. You can manage your project, and the project is called a workspace. Okay, now everything will be inside a workspace, right? Your data display window, your data sets, right? Your designs, everything will be inside a workspace. And this workspace, if you see, would have underscore work. So whenever it says new workspace and it says you give a name, you leave this intact, because this helps ADS system to know that this is an ADS workspace. If you remove this, it might complain that this is not an ADS workspace. So it's in the name. So don't edit this when you make a new workspace. Leave this underscore work as is and then give a name. And in the name, you cannot use white space character. Actually, you can use white space characters, but when you do simulations, you might have problems. Okay, might have problems. Similarly, if, for example, let's show you, let's switch off the annotation part. Okay, similarly, if I have, for example, let's look at a directory structure. Okay, now how do I clear annotation? I never use this clear annotation. There should be something to clear annotation here. Clear our drawings. Okay. Okay, so over here, if you look at in the file system, everything goes, unless you change it, everything goes to users. And in users, there are folders. Like, for example, this is what my machine is called, right? So if you look at this, you will not see any white space characters, right? So it's advisable to have a directory structure where white space characters are not there. For example, I could have made a new folder here, and I could have called it Anurag space Nigam. That's perfectly valid. Okay, Windows doesn't have a problem with this, but ADS has a problem with this. Okay, once you do start doing simulations, somewhere it'll break. Okay, so I would advise in the entire paths, okay, don't use white space characters. You can use underscore. For example, I can always put here Anurag underscore Nigam, right? So this is valid. Or in your naming also, I can put underscore. Underscore is valid, but don't do white space characters, because later on you might have a problem with your workspace. Okay, so that's what is advisable. Okay, so right now I am inside this folder. All the projects are going to be here. Now, when it comes to installing a PDK, okay, earlier you used to install it. Now you just copy it. For example, we are going to use this PDK. Okay, now this PDK is a GPDK or general PDK. Okay, so what is in there? Okay, this is a compiled version of PDK. Now, does it mean that you cannot touch the models? That's wrong. You can touch the models. So for example, now this is something which I'm showing you because I don't want you to get restricted. Okay, so let's admit. I don't want you to get restricted that, you know, we don't have a PDK and stuff like that. Okay, so I'll show you where they are. So if you go here, models, and if you go under Spectre, so basically it is basically imported from what you saw. That's why the models are residing here. Now, if I open a model, for example, NMOS1, okay, so let's use a notepad. Okay, so this is the model. Now, there is nothing which avoids you from changing anything. For example, these are your constants, right? Now, these are your bins. Okay, so this is nominal, this is slow, this is fast, and then there is a statistical distribution here, right? So if you want to do Monte Carlo analysis, all these variations are statistical distributions. You can change them, right? And then, so this is the statistics. Now there are functions like, for example, Gauss. So if you know AEL, okay, application extension language, you know where, you know, how to call this. You can write your own functions, right? So what am I passing to this? I'm using a Gaussian function and I'm passing a standard deviation for that model for a particular parameter, right? So these are process variations here. So statistics. Next is, these are your spice models. So if you look at this one, this is your BSIM3 model, right? BSIM3v3. Okay, and so this entire thing you can copy from Cadence, right? If you want, you can copy from Cadence, and that would be valid. But then you should know the switch. Okay, the switch is, if the gate length is between this and this, then you are going to use model 1. If the gate length is between this and this, then you are going to use model 2. So this is called binning. Okay, so if you want to take a compiled version of PDK also, you would be able to do your own devices here. Same thing is there for, let's say, diodes, right? Same thing is there for, let's say, resistors. So this is a resistor, right? Capacitors. Okay, all models are in here. Okay, now before you touch any of the, what you call this, okay, there would be something called restrictions, in the sense when you do DRC, there will be DRC rules. So now if this is a 180 nanometer process, that means that the minimum gate length is 180 nanometers. Now I decide I want to do 90 nanometers because my model is 90 nanometers. Then you should see where the switch is, like, you know, the DRC rule file, right? So the switch is somewhere here. HF, HPE, hang on. The switch is not preference files. Over here, let's, no, this is ADS, no, these models are not used. Tag files, okay, tag files, rules. Let me see if I open this. Okay. Okay. Now here, there will be certain switches here. Like, for example, they won't allow you to have what you call a length less than 130. But then in the file, you would find a location where that is there. And you should be able to change the min and max. You can even change the DRC rules here. Now, I wouldn't recommend that. Okay. Why wouldn't I recommend that? Because this is a fictitious process. You can change everything you like here. Okay. But then in a real PDK, you are not supposed to change it. Okay. So how come this library, which was 5 gigahertz, now works at 27 gigahertz? Because this is a 130 nanometer process, though it says 180. And everywhere I have changed the minimum sizes, right? So that the DRC doesn't complain. I can write the rule files here myself. Okay, so I can go ahead and write the rule files myself. Okay, so what I'm trying to say is, PDK is a software, and a software can be modified. Even if it is a compiled version, there are text files from which it draws the input. So if you can modify the text files, you have modified the entire PDK. Okay, so that is what has allowed me to do a 27 gigahertz design here, and the process is called Silterra. And though this is the PDK I'm using. Now, somebody might question, why am I modifying this thing? Okay, let's take a break of 1 minute because there is some background noise. I'm going to put myself to mute. Okay, I'm sorry for that. Back to where we were. Okay, so even if it is a compiled version of a kit, you should be able to change the text files. You should be able to change the models. So there is nothing which will stop you. Now, why did I still stick to this GPDK? Reason is it allows you to do the layouts, the layers, the via layers and the metal layers and stuff like that. Then there are thermal models in this. So I wanted to make a kit which can be used by everyone. There is no restriction. Okay, I will address the question in a bit. Let me see what's the time right now. 10:41, 5 minutes. Okay, so we are able to modify whatever we want in this stuff, right? And most of the stuff will sit under models. And if this is just a ADS kit, the models will sit here. If it is imported from, let's say, Aldo, the models will sit here. If it is imported from, Spectre, from your ADS, the models will sit here. So this in configurations file, it is set where you are going to draw your models from. Okay, you can set that in the configuration file itself, right? So you can set that there would be a config file here. I think there is a config file. Okay, from the config file, I think it mentions here where it comes from. Okay, it says path, fill patterns, and everything. It shows, actually, this is not the one, but then there is a config file which shows where the models are coming from. Let's see under models. No, it should be under here. CDS lib tech file. Tech file, it should mention here somewhere. It has been some time. I changed it. These are your various physical layers and non-physical layers here. Okay, why am I showing this? It's just that I want you to have a kit, and the kit is the major bottleneck, right? I want you to have a kit to experiment. So that's why I'm showing you this. You can take a demo kit and modify it to your requirement, right? You can prove your concepts here before moving to a realistic PDK. So that's the whole idea, right? And I think Keysight guys wondered, how did I do a 27 gigahertz on a 5 gigahertz kit? Because I changed the models, right? I did my own modeling, right? So that's there. Now, coming to the questions. Cadence is usually integrated with ADS momentum. No, it is not. Okay, Cadence has a method of moment. So method of moment is a technique. Momentum uses method of moment. So basically, Cadence might use a method of moment technique, but it is not ADS integrated into Cadence. It is a 2.5D or 3D simulators. Okay, momentum or method of moments basically is always 2D simulation. Okay, method of moment means that you are treating everything as a thin sheet, and all the meshing is done in sheets. Okay, and then the Z currents or Z currents are basically mathematical fudging. Okay, so they call it 2.5D, but it is not a 2.5D. It is 2D with some add-on. Okay, you call it 2.5D. Okay, next thing is 3D simulators. Okay, 3D simulators are, method of moment is not a 3D simulator. Okay, any thing based on method of moment is not 3D simulator. FEM, finite element method. Okay, or any modification of Galerkin's method. Okay, whether it is FEM or whether it is any FEM or any other method, it is a 3D method. The meshing is 3D. The meshing is adaptive. Okay, and then there is something in FDTD also. The meshing is adaptive. Okay, there's something called current factor S. Okay, current factor is basically a dispersion when you go diagonally in a cell, right? So these things are there in 3D simulator. So FDTD is a 3D simulator. Okay, FEM or FEM is a 3D simulator. Method of moment is always a 2D simulator with some fudging. And Cadence has a method of moments, but it is not momentum. Okay, if you want, you can take the touch tone file, or what you call S2P file, from here onto cadence. For example, inductor, you simulate in momentum and take it touch tone file into cadence. You can do that. HFSS says it's a 3D simulator. It is a 3D simulator, right? It uses FEM, right? So that's a 3D simulation. Now, here, let me add very quickly a note. Okay, where do you need what you call FDTD and where you need FEM? If you want to have a very large volumes, okay, then you should use FDTD. If your volume space is small, it's a frequency domain technique, FVM. You should use FVM or FEM. If the thing becomes large, you can do like multiple wavelengths. Then you use FDTD. And then discretization in FDTD is also now not a uniform one size cell. You can have a different cuboidal cell, different size cuboidal cells. And then you can do this, that you can move from one mesh to another. It also allows you to do what you call parallel MPIs. That's why FDTD is used for parallel simulation, because it is very easy to do multi-processor simulation, right? So FDTD is a time domain technique. It is not a frequency domain technique, and it can handle large volumes, right? So you should use FDTD when there are large volumes involved. When the problem space is small, you should use, for example, a package design. You should use FEM. Now, method of moments is good for planar circuits. As soon as you put a 3D to it, then method of moment is not good. Like, for example, let's say VIA, which is basically conical. You cannot use method of moment. It will be an approximation, right? And then the surface currents, for example, let's say antenna, okay, the back plane is ground, right? Now, that ground currents are very important, right? Now, if that is fudged, right, then the antenna will not be accurate, in a sense that it will have a lot of back lobes and stuff like that is momentum. As soon as you simulate this in EM Pro, you will see that those back lobes which you are seeing were not there, right? This is because the ground distribution is an approximate one. And that is very important when you make broadband antennas, like, when you cut slots in the ground plane, when you use EBG structures. Okay, better use FEM. Don't use a method of moment for EBG structures. Okay, so I guess I have answered your question here. So let's take a 15-minute break, as we have crossed 10:45, and we come back here. You leave yourself logged in. Okay, and if you have questions, meanwhile, you can type in the chat. I will still be happy to answer your questions, right? After that, we will get started on the real IC design. Okay, so let's meet at 11 o'clock. You have a small break of 15 minutes, and I would be happy to have you back. So let's have a break of 15 minutes.
Official's decision is final. But now, great. From our point of view, we couldn't really see Corey. To your point, but now the point of view.
Hello?
Hello. Yeah. So what I was saying is that if you have any questions, I'm ready to take questions. So I have unmuted all of you so that if you can ask me a question if you have. I'm going to be here. Those who want to take a 15-minute break can take a 15-minute break. Can you enlighten us on cadence with an analogy to ADS? Nidhi. Yeah. Nidhi, can you ask me a question because I need a little input from you. What you mean by analogy to ADS? Nidhi?
Hello.
Yes. What's your question?
So, like, I want to ask, like, usually what we do in ADS, we do circuit simulation, then we go to the EM part, and
Yeah.
then we do EM simulation, then circuit simulation. But when it comes to CMOS, we usually talk about cadence where we use virtuoso, spectrum,
Yeah.
this mentor graphics. So these all terms are a little bit confusing to us, usually for
Okay.
users.
Okay. Let
So
me explain you this. Okay. Fine. I heard your question. I understood your question. Let me explain you what's happening.
thank
Okay.
you.
Circuit simulators, right? And versus the EM simulators. Now we can do co-simulation. Co-simulation means that all the passives, okay, passives can be simulated in EM simulation, and then those results can be brought into circuit simulator, and then the whole thing can be simulated. So that means that passives, you do not have to model them. You can have a EM simulation on that and bring the data set file into circuit simulation, and you should be able to do a co-simulation of circuits along with the passives. Now, in EM simulations, we should know one thing, that EM simulators are Laplacian solvers. That means that the source, the free charges moving are not there, in the sense that, of course, current estimate is there, but then you will not put charge into the substrate. You will not put charge as a source of fields. Okay, so it is like I will not say lossless. It is a source-free medium, which means that I'm not injecting electrons or holes into my volume of simulation. That means that it's a Laplacian solver, right? So I would not be able to do actives. Okay, so if I cannot do actives, then that active part, which is basically transistors, diodes, and everything, how would I include this in simulation? Okay, so that is the circuit simulation. In circuit simulation, there are models for transistors, for diodes, and all that stuff. Okay, there are models for passives also, but then circuit simulation means that we can use active devices, models for active devices through circuit simulation, and then we can take passives from EM simulation and put them together as a one simulation space, right? So that's the two-step solution. Take the passives, simulate it in EM, get the S parameter files, put them into circuit simulator, and simulate it along with the actives. So passives are simulated along with the actives. Passives are simulated in EM simulation because EM simulation is a Laplacian solver, and then actives are modeled in circuit simulation. So actives are models; they are not the actual devices. Okay. Now, if you want to do both in one simulator, it is going to be very elaborate. For example, if you want to use ISC TCAD, or if you want to use Centaurus TCAD, what you call, or if you want to use what is called COMSOL, right? So for example, I'll show you. Okay, for example, COMSOL. So if I want to use COMSOL, Okay, so console will allow me to do passives along with the actives, right? I would be able to do a transistor, and also I would be able to do passives attached to it. Okay, so I can do multi-physics study. Multi-physics will be, I would be doing EM simulation along with the semiconductor simulation. Okay, so those are called multi-physics simulators, like COMSOL or Centaurus TCAD, right? So that will allow you a one single simulation, uniform simulation, where there are no two different simulators working together, right? But then that is very elaborate. Now, do industries use it? Yes. So for example, a processor, which Intel does, Intel will do a full chip simulation on TCAD, right? For the entire chip, which includes the physics being simulated. So like, for example, here, let's say if I have an open here, and let's say if I have a thing available here, why going to key site? I should go to documents. For example, let's look at a MOSFET. Okay, so now this one, sorry. This is like, okay, so this is your finger for a MOSFET. Okay, so there is a source, there's a drain, and there's a gate, right? So this device is simulated. Okay, so this device is simulated in COMSOL. A COMSOL will allow you to do charges like electrons and holes, right? So I'm simulating electrons, right? So COMSOL will allow you to do that, right? Let's say you can even have a look at it. Okay. Okay, for example, I can see various excitations, and I would be able to see the electron flow and stuff like that, right? Why is it so slow? Okay, it is computing. Okay, just 1 second. Okay, so can I put it in a loop? Can I put this in a loop? Yeah. And then I put a play. Okay, so you see here that I have a channel which is forming, right? And then this is my what you call the channel length modulation. You can see this kind of stuff, and you can simulate the electrons and holes in multi-physics solver. You can at the same time do inductor. You can basically do elaborate circuit. You can do an entire chip in here. But then this simulation is going to take very long time. And memory requirements are very large too, because there will be like lots of devices. So I have done maximum up to like 15 devices together in a circuit, along with the passives and actives. So this is possible in a multi-physics simulator like COMSOL, right? But this is not possible in EM simulation, which is a Laplacian solver. This is a Runge-Kutta method-based solver. It solves ODEs based on that, right? While Helmholtz equations are solved in a Laplacian solver based on some of the techniques like method of moment, FDTD, and all that, right? So different simulators are for different applications. EM simulators are for EM simulation where there are no electrons and holes, right? Okay, so I guess I answered your question. Now, different tools are trying to attempt the same stuff. For example, ADS, right? It has a method of moment or FEM or let's say EM Pro. It will allow you to do EM simulation in their tool, bring those results into circuit simulator like HB or transient, and then do a co-simulation, right? Same thing is with Cadence. Cadence has a EM simulator. You will be able to simulate inductor, but then you will be running a circuit simulation with text file as an input for your S parameters. Okay, so there is no confusion here. You would be doing a two-step solution, doing EM simulation on passives, bringing those passives into circuit simulator, and then simulating it. Okay, This is with everybody. This is with everybody other than the multi-physics simulators like Centauros TCAD and COMSOL and stuff like that. And then there is CoVentorWare. Okay, so there are lots of other tools are also there which will allow you to do both. But then the simulation is going to be very time-consuming, resource-consuming. Okay, so all things are available to you these days. Okay, so have I answered your question, Nidhi?
Yes, sir. Yes.
Okay, can you enlighten Cadence? Okay, if I'm using Cadence, when do I really need to shift to ADS? Okay, it's like this. In Cadence, if you are used to Cadence, everything is easy in Cadence. Okay, but if you are not used to a software tool like Cadence, then the easier thing is ADS. Why it is easier? Because to set up simulation is easy. Otherwise, you should know what is analog artist, you know how to set that, and then how to plot and stuff like that. Once you learn that in Cadence, it's like Cadence is like your second nature. You are so used to it that you don't like ADS. ADS looks childish to you sometime. Okay, but if you are new, it's easy to set up simulations, to design circuits, and to analyze the output, to write equations or for post-processing, to write equations as variable equations, to model things with equations like equation-based linear, nonlinear models. It is very easy to do in ADS. So if you are a beginner, right, you can use ADS to get used to. And there are lots of things which are difficult to do in Cadence. For example, if I want to write an equation in a parameter in a circuit, okay, then I should be an experienced user of Cadence to be able to use that. Even if I have to declare a variable which is tunable, okay, so I have to use something called param or something like that, a keyword, and then put it in bracket whatever you want to vary. Or in your analog artist, you have to read that variable, set the values for variable. In the ADS, it becomes very easy. It becomes everything is like a slider. You declare a variable, slide the variable, and it will change automatically in the circuit, and you will see the results. So things which are easy to do in Cadence, in ADS, okay, you will struggle to do in Cadence. And what you are doing is you are trying to learn a concept. So once you want to learn a concept, you want the tool to be easy on you. So that time ADS is very good. Okay, when you're doing very complex things, you don't want to struggle with the tool, right? You should be having a very easy interface. So that's what ADS is. Okay, it provides you an ease of implementing everything. And if you know post-processing, in Cadence, post-processing is going to be very difficult because there is a calculator there. There are some functions which you can write there. It's through that. While in here, there is a data display window. You can write anything what you write in MATLAB, you can write here, because it uses the same Rfic and BLAST libraries, right? So that's the advantage of ADS. Okay, could you please record all the sessions 5 days so that we could revisit? I am going to do that. Okay, I am doing that actually. Okay, it will become big. What I'll do is I might put it on YouTube, and then you can see there. Or what I can do is, let me mute all of you unless you have a question. Okay, or what I'll do is I will put it on a FTP site on my website, my company's website, and provide you with a password and username, and you can download from FTP site the videos. So in YouTube, what happens, the resolution goes bad. So for this, what I'll do is I'll put it on a FTP site, and you can download from there. So I guess I solved your problem, right? Okay, now all of you are welcome back. It was a short break, and I don't want to hammer your brain right at the start. I want to generate the interest first before I start hammering your brain. Right, so we will have a good lunch break, so don't worry about it. Okay, so I guess I have explained to you what's a PDK. Now let's get started with the real stuff. Okay, and the real stuff goes like this. So I need to explain you the difference. So let's look at the second part of this. Okay, I will download this. I will rather put a PPT. I'm always going to the LinkedIn to find this, which is wrong on my part. Okay, I'm over here. Okay, so the next is analog versus MMIC versus RFIC, CMOS, SiGe, gallium arsenide, GaN, Mosfets, PHEMs, and HBTs. What I'm trying to do here is compare. Now, if you are working for an organization, and the first question comes to you is, I am going to use a process. Which process should I use? Now, should I go with the hype? If everybody is using gallium nitride, should I be using gallium nitride? Right? Or why should I be using CMOS? Or where do I need CMOS? Or where do I need BiCMOS? Right? So those questions I'm going to address here. Okay. So first topic here is, let me see if I can magnify this. Is there a way I can zoom in? Or I can download this. I have to download this, is it? Save as. It will save as a HTML, which I don't want. Okay, anyways, I'll get it. So the point is clear. I'm going to compare analog, RFIC, MMIC. You should be clear about what domain you are working and what are your limitations. Because when you do transceiver, at one point, you are interfacing voltage mode circuits with the power mode circuits. And they are designing that interface is very critical. You will lose most of your gains and stuff like that. So that's why you should understand what is the analog IC, what is RFIC, what is MMIC. Okay, let me down this. Okay, should be able to write somewhere. Okay, should be able to tabulate points. Okay, analog IC. Okay, in analog IC, okay, the circuits, okay, they are either voltage mode. What does that mean? That means that all the nodes in the circuit, they are high impedance. Okay, nodes are high impedance. Okay, that means that the voltages are swinging while the currents are low. Okay, so in a voltage mode circuit, the nodes are high impedance, currents are low. Most of the swinging is the voltage swinging. Okay, now then you can have a current mode circuit. In current mode circuit, all the nodes are low impedance. Okay, and voltages are low. So all the swinging is the current swinging. Now then there are mixed mode circuits, which you will also call as power mode circuits. Okay, which means that not only the voltage is swinging, but the current is swinging. So voltage as well as current is swinging. Now this results in impedances. So whenever I do V by I, that would be the impedance, which is a complex number. Okay, so in a mixed mode circuit or a power mode circuit, I am dealing with nodes which are not very high impedance, not very low impedance, but somewhere in between. So these are called mixed mode or power mode circuits. Now this voltage has an angle to it. Okay, so let's so basically this is a complex number. Because voltage to current ratio, there would be angle difference. So this will not be a real number, but it will be a complex number. So basically we are dealing with complex voltages and currents. Okay, next we would have V into conjugate of I. Okay, so that means that this is a power. Okay, so there is going to be a real power. A real power is going to be half of real of V into complex conjugate of I into complex conjugate of I. So this is a power mode circuit. A power mode circuit means that there is going to be impedance, which is complex. There is going to be power, right? V into complex conjugate of I. Right. So in power mode circuits, you have both. Okay. So analog ICs are going to be mostly dealing with, these are analog ICs. While this is an MMIC or RFIC. So let's make it red color. So now we are very clear. Analog ICs, I'm dealing with voltage mode or a current mode circuit. While MMIC and RFIC, I'm dealing with power mode circuit. Okay, so this difference should be very clear. Now, if I was to integrate a voltage mode circuit into a power mode circuit, so if I want to cascade a power mode circuit with a voltage mode circuit, this usually happens, okay, in a transceiver design. In that case, you will lose a lot of gain, because if you see over here, the power is zero. Ideally, if the currents are zero and only voltages are swinging, then the power is zero. Right now, you want to put a zero power into a power mode circuit. That means that, of course, the inputs are very small, right? So all the voltage gain which you are seeing has trickled down to some kind of a power gain. So you are going to use a lot of gain doing this, or rather, you are doing a lot of impedance matching. You are going from a very high impedance to something like a 50 ohm impedance. So whenever you make a transition like this, if you do not match it properly, you are going to lose a lot of gain. Okay, so this basic difference you should understand between analog IC versus RFIC or versus MMIC. Now, the question is, what is the difference between RFIC and MMIC? Okay, RFIC, I'm mostly referring to CMOS, which means that there is a P-channel MOSFET and an N-channel MOSFET. So there is a pull up and a pull down involved here. Okay, here we are not dealing with PMOS device. Now, the reason is very simple. The reason is in CMOS, which is a silicon process, okay, the whole mobility is roughly 2.5 to 3 times of the electron mobility. So we can have both devices. We can have a PMOS device as well as an NMOS device. While here, like for example, gallium arsenide process, okay, the whole mobility is roughly 1/80th, roughly. For example, gallium arsenide, okay, much slower holes are there. So basically, whole mobility is much smaller than the electron mobility. So that's why you do not have P-channel devices here. Then you have only N-channel devices. So if you want to make logic, for example, using N-channel devices, so it will be resistors as pull-up resistors and the N-channel device. Okay, so all the circuit would be designed as a N-channel device circuit with resistors for pull-up or resistors for load. So that is MMIC. RFIC, you can have a pull-up device or a current mirror as a load. Okay, so current mirror, as soon as you put current mirror as a load, then the frequency basically goes down. So for example, if you make an op amp, right, or let's say OTA, okay, the frequencies are going to be much smaller, right? Now, if you want to make a high frequency circuit in RFIC, you will not be able to use PMOS. You will have to use resistors, right? So let's say there are differential stages, right? So now the question comes is, whether the circuit has to be single-ended or differential. Most of the circuits over here are single-ended, means that the signal has a ground reference. Even here, the signal has a ground reference, right? Here, the circuits can be single-ended as well as differential. Now, the circuits are differential for a reason, okay? For example, if you take any single-ended circuit, it needs a bias point, okay? And if the gains are very large, and the bias point is fixed, so the gain is only for a very small input voltage range. So when the gain is for a very small input voltage range, let's say the bias point drifts. For example, let's say common source amplifier, or let's say common gate amplifier. Okay, it is a single-ended amplifier. But if it has a high gain, then the input voltage range is very small. So the bias point should be at the center of that input voltage range to have a sufficient gain, right? So here what happens is that voltage can drift with temperature, can drift with process, can drift with aging. Okay, so it is not advisable to do a high gain stage with single-ended circuits. Then you put differential circuits. Now, as soon as you put differential circuits, the noise is solved because the common mode noise basically goes away because common mode gain is very small. Now, if you make differential circuits, there's another advantage. The common mode input voltage range is large. Okay, what it means is that even if your bias points drift, okay, you are in a very large common mode input voltage range. So nothing happens to you. Circuit behaves the same. So for example, let's say if I put a OTA or an op amp, the input voltage range is going to be almost 2/3 of the supply. Okay, that means that your bias is not so stringent. Okay, as long as the supply is sufficient headroom, you would not run into transistors going out of saturation. Okay, so differential circuits you see everywhere. Actually, differential circuits you see here, here, here. But then the differential circuits have two advantages. One, the common mode noise is cancelled out. Second is the common mode input voltage range is large. Okay, so that's why you do differential circuits. But then differential circuits have their own restrictions. The restriction is in systemic in offset voltage. So if you have a differential in and differential out, then you need something called a common mode feedback circuit. Okay, which can be again a linear common mode or basically it can be a digital common mode feedback circuits. Okay, so there are restrictions. Okay, as soon as you go to differential circuits, if you have a resistive load, then you can still go to very high frequencies. But as soon as you put a PMOS load, like a current mirror or something, then you are restricted to a low frequency, right? Now, all this is changing again. When you go to FinFETs, for example, the devices can go up to very high frequency. So basically, it really doesn't matter whether you are doing an analog circuit or an RF circuit, because FinFETs will allow you to do circuits in gigahertz, right? So you can have an op amp which can work at 10 gigahertz in FinFETs. So that's okay. So these problems, what you call these differences are basically minimizing as we go ahead in technology, right? So but then in the IC, you might have to design everything. Like for example, let's say if you design a RFIC or MMIC, you have to design a power circuit, which is temperature compensated, let's say. So then you will go to some kind of analog circuitry to design a power circuit, right? So it may be a band gap or a PTAT or a CTAT or something like a threshold referenced, VT referenced circuit, but that's analog circuitry. So when you design ICs, you are supposed to know most of the stuff here, right? So you should know something of analog IC, you should know something of RFIC, MMICs, depends on what frequency you are working, right? So basically this difference is minimizing with the time, with the technology. But analog ICs necessarily means voltage mode or a current mode circuit, while RFIC, MMIC means they are power mode circuits. Mostly these are single-ended, but you will find differential also. Mostly these are differential. You'll rarely find single-ended implementation, right? So this is a basic difference between analog IC, RFIC, and MMIC. Now, comparing RFIC and MMIC, mostly this is CMOS. Okay, mostly this is going to be gas. Mostly this will have a PMOS device available to you. This will not have a PMOS device available to you. Now, the question comes is CMOS versus BiCMOS. Okay, now you know that there are two transistors, right? So let's put here a new slide. Okay, CMOS versus BiCMOS. Okay, now you should understand the difference between two broad categories. One is called Mosfets, and the other one is called HBTs or BJTs. Okay, now Mosfet, if somebody asks you what is a Mosfet, it is a voltage controlled current source. Simple. So a MOSFET is biased with a voltage. A MOSFET is a voltage controlled current source. That's why we talk about transconductance. Why? Because the output is a current, input is a voltage. So we are talking about transconductance GM. Okay, so the first point here is MOSFET is a voltage controlled current source. That means that you can make a voltage mode circuit or a current mode circuit. So this is a basic element for analog circuits. Okay, this is a basic element for analog circuits. Now, so this is biased. Okay, so this is biased with a voltage. Okay, now this can also be biased with a current if you are using current mirror load. Okay, biased with current while using current mirror load. Now, you still require a DC voltage, right, at the input, a bias voltage, and then you will put a signal around it, right? So basically it is biased with a voltage. Okay, and what it matters to you is a voltage swing because it's a voltage controlled current source. So your input is a voltage. Now, if, for example, I design a power amplifier using MOSFETs, okay, now what is the restriction? Okay, can I just increase the size and say that, like, for example, let's say I have a 1 millimeter device and 1 millimeter device. So let's put down these differences also. Okay, 1 mm device. So what a 1 mm device can do, if you are in a gas, gallium arsenide, then the power density is like 200 milliwatt. So 1 millimeter device would deliver 200 milliwatts. Okay, so what 1 millimeter is? It is gate width. So this is width. Okay, length is the minimum what you can use. So this is what for gas. Okay, now what a 1 millimeter device can do, what a 1 millimeter device can do for a GaN process. Okay, it can do most of the processes, it can do 4 watts. So this is GaN. Okay, now this is there. Now let's look at what a CMOS thing will do. Okay, we are talking about 80 milliwatts or something like 60-80 milliwatts, 60 milliwatts or 80 milliwatts or something like that. It can go up to 62, let's say. It can go up to 62, 200 maybe. This is your CMOS. Okay, first thing first, clear. Okay, now when I am fixing the width, I am I'm fixing the channel width. Then I am limiting Imax. Okay, I'm limiting Imax. Okay, now if I want to take power up, okay, so if I want to increase the delivered power, okay, what options do I have? Because the channels is fixed, the bias is fixed. So as soon as you fix the voltage bias, you have fixed ICQ. So as soon as you fix the bias, you fixed ICQ, right? Okay, the quiescent current you have fixed. Now when you start hitting it with power, the other constraint is VDD. So these are your two constraints. Okay, so these are your two constraints. Okay, now why they are the constraints? Let me plot current versus input power, or let's say output power. Okay, so this is there. Okay, you can plot it yourself. Okay, what you will see is the following. You will start with a quiescent current, and as the power goes on increasing, your currents will go up. but then it'll saturate out. Okay, so if this is ICQ, sorry. So if this is your ICQ and this is your Imax, okay, so this is your Imax. This is usually 2.5 times or 3 times maximum. Okay, so it doesn't allow you to RF bias so easily because it's a voltage mode circuit. The way this current has gone up is because of the voltage clipping, okay, on the input side. So this is a voltage clipping on the input side which has taken the DC voltage up. So that's why the current has gone up from ICQ to Imax. And this is usually 2.5 times to 3 times. I would say 2.5 times is the best you can do. Okay. Okay. So now if you hit it with power, so let me put the x-axis here as input power. This is what is happening in case of a MOSFET. So if you use a MOSFET for designing a PA, you can design like this. What you can do is you can say that I want to deliver, let's say 3 watts. Okay, so let's say, for example, I want to deliver 3 watts from a supply voltage, which is 3 volts. Okay, so if you look at this, what currents do come in mind is 3 by 3 is what? 1 ampere current, right? So that comes in mind as 1 ampere current. Now, what can happen is usually the efficiency of amplifiers is around 30 to 40%. So let's assume 30%. So let's go 3 times. So if I want to deliver 3 watts, I would be consuming roughly like 8 watts. Okay, so if I'm consuming 8 watts DC with the efficiency of roughly 30%, roughly 30% efficiency. Where is percentage sign? Come on, what's the keyboard here? Okay, so if I want to deliver 3 watt as P out, okay, from a 3 volt, I am basically delivering 8 watt at 30%. I'm taking this much from that. So this 3 divided by 8. So my current I max is going to be equal to 3 by 8 amperes. Then my ICQ is 2/5, right? So ICQ is going to be equal to 2 by 5 of, where is the multiply sign, of Imax. Okay, so basically you have a quiescent current like this. Okay, so now if you want to take the power up and you have a restriction on Imax, then the only thing which is left for you is this. Okay, you can take the power up by increasing the supply voltage, or you can take the ICQ up. You can take the ICQ up, or you can take the voltage up, because this is a voltage controlled current source. That's the major limitation. You are clipping voltage on the input swing. That changes the DC value. That basically takes the current up. Okay, but then it is roughly 2.5 times. Now, if you want to go for a larger power, do I need to, for example, if I want twice the power, should I just make the transistor to be twice the size? Well, not exactly, because it is a voltage swing. It is biased with the voltage, not with the current. It has to do with the quiescent current, right? Of course, you can work with start with the power capability. Okay, how much maximum it can deliver, right? So these are the limitations when you design a PA with a MOSFET, FAT, PHAMT, or any HAMT technology, or any, sorry, FAT technology, where there are like field effect transistors. Now with BJTs, it's a different scenario. Why? Because it can be both. Okay, BJT can be this is a true power mode device. True power mode device. Okay, so let's put it on the left side. So it's a true power mode device, which means that this is a voltage controlled current source. Okay, so it can be a voltage controlled current source. Okay, it can also be a current controlled current source. Okay, so now there are two ways of biasing BJT or HBT, whatever you call it. Okay, you can bias it with the voltage and bias with the current. Now there are two differences in this. There are two major differences in biasing with the voltage and biasing with the current. If you bias with the current, then the condition is like the breakdown conditions is like collector to what you call ammeter breakdown with the base open. Collector to ammeter breakdown with the base open, because you are biasing it with a current source. So the breakdown voltage is going to be, so in this case, the major limitation is, okay, BVC collector to ammeter breakdown with collector to ammeter breakdown with base open, which is going to be BV collector to base breakdown with ammeter open divided by 2, which means that rather this will be beta. Sorry. So let's say the beta is 100. Okay, and the breakdown voltage here is 14 volts. So 100 by square root of 100, which is 10. So 14 by 10. So BVCEO is 1.4 volts. So if you bias a HBT with a current source, your breakdowns are going to be much earlier. Okay, because of thermal runaway, right? Okay, now if you bias it with a voltage, okay, then you are seeing 14 volts. So there is a problem, there is a difference here. You bias the BJT with a current versus bias the BJT with a voltage. If you bias it with the voltage, your breakdowns are higher, right? If you bias it with the current, your breakdowns are lower. Now, if you bias, then you would say, why don't I just bias with voltage? Well, the answer is linearity. Okay, so if you bias with the current, it will be more linear. If you bias with the voltage, it will be less linear. So that's the difference, right? Now, can I have something in between? Yes. Okay, so that's the IBM patented technology. What you do is you hang what you call a diode connected transistor on the base to the ground with a resistor, and you can turn on that device at any power level you want by scaling the resistor. So this is something which a book will not teach you. So let's say if I bias it with a current and I put something like this. So let's say very simply we put, this is my transistor. Sorry for wasting your time. So this is my transistor. And what I can do is I can connect another transistor over here. And how would I connect this? Okay. So I would connect a transistor hanging here. Okay, so this transistor would hang in here. Come on. That's why I should use a pen. So just bear with me. I will turn on that feature also. Okay, what I can do here is I can put a resistor in between and bias it like that. So I can put here a resistor like this. And then I can put a ground here. So assume that there's a ground here. Now I bias this with a current, right? And then this resistor basically decides when this device is going to turn on. So when the thermal runaway starts, that means that the base current will turn negative. So as soon as the base current turns negative, I turn on this guy. So then all the current, which is a negative base current, flows through this device instead of going into collector base. That stops the runaway. So the breakdown voltage is no longer this divided by square root of beta. The breakdown voltage is much higher. Okay, it is of the order of this, because I am taking all the negative current and putting it in this device rather than it going through the base emitter, which will again see a beta and a runaway. So this is something which is a IBM patented technology, right? This is what you do when you bias it to the current for a higher linearity, but you want to protect the device with a higher breakdown. So when you design a PA with a HBT, this is what you would do if you bias with the current and want linearity out of it. This is not what they teach in the books. This is what you get it from the industry. Okay. Next thing which you do is there is a major difference here. Okay. The major difference is the thermal stability. Okay, between a MOSFET and a BJT. Okay, so for example here, it is a voltage mode and a current mode device. It is a power mode device. So what you are putting in is a power. Okay, now if you have a supply voltage and voltage is fixed, then you can still keep on putting the power, and you can still increase power at the output, and it will compress. It will compress to any extent. It will compress by 14 volts if you want. Here, you cannot compress this guy to that level. It will blow up. Okay. Usually, when a MOSFET goes into compression, it usually becomes unstable. You have to stabilize it. In PAs, you run into this problem all the time. You come into this problem of the MOSFET blowing up under power, because it starts oscillating, and you have to stabilize under compression, which you do not have here. In BJT or HBT, you can keep compressing like anything. It will not complain. That's the difference between, when you design something like, RFMD is designing something with MOSFETs here, and IBM is designing something with SIGE here. So if you go to their booth and you say, oh, show me under power, show me a mismatch, or operate it cold, this guy would blow up. RFMD would have a blow up part. You go to IBM booth, ask them to do this with their SIGE, it will not blow up. It is very rugged. Okay, so when you are a PA designer, you are going to see these differences. Again, there are lots of differences on HBTs. Okay, so for example, in MOSFETs, what variations do you have? Okay, or some kind of FETs, not MOSFETs. FETs. Okay, mostly the FETs can be MOSFETs. Okay, or what you call LDMOS. Okay, and then they can be also PHAMs or HAMs, or PHAMs, or junction FETs, what you call junction FETs, or rather MASFETs. Okay, and then you have got PHAMs or pseudomorphic HAMs. Okay, so this is this category. Okay, and over here you have got HBTs. And what are HBTs? There are different flavors. SHBT, or single heterojunction HBT, which is a base emitter junction as a heterojunction. Or it can be a DHBT, or both both junctions are heterojunction. The collector base as well as emitter base junction are heterojunction. Now, what are the advantages? Actually, what you are trying to do here with heterojunction is tailoring beta. Okay, the base emitter junction is forward biased. The base collector junction is reverse biased, right? This forward bias junction, the electrons are flowing from emitter to collector, while the holes are flowing from base into emitter. So there is two components to base. One is the recombination current, other is the base emitter current. Now this base emitter current can be brought down with a heterojunction. So when you bring that down with a heterojunction, beta shoots up. So basically HBT is for a heterojunction on base emitter to improve beta of the device. Okay, so that's what happens with a heterojunction. Now, there are other technologies in which, for example, in silicon germanium, you can have a double heterojunction, because over there on the other side, you are trying to avoid some kind of a collector collapse. Okay, so the base collector junction can be a heterojunction to enhance the breakdown voltage. Okay, but then there can be other things. So for example, in a channel, the maximum oscillation frequency, or the FT of the device, depends on the base transit time. Now the base transit time can be increased. Okay, this can be increased by what is called pseudomorphic, what is there in silicon germanium. So you can do a silicon germanium in the base, and in certain direction you can accelerate electrons. So when you accelerate electrons, then the FT of the device goes up, base transit time comes down. Or the other way to do this is, okay, I'll come to this question. The other way to do this is you do what you call a triangular or a pentagonal germanium doping in silicon base. That way you can set up a quasi field, E field, to accelerate electrons in the base, and that the base transit time goes down. So this is a patented technology of IBM, again, triangular profile. If you go with the pentagonal profile, then that would be a patented technology of Mmic Germany, or ISP. Okay, so you should know the process for your application. Okay, and these limitations, they come in when you blindly choose your process. You cannot do that. Okay, so if I use SIGE, I would again be choosing between ISP and global foundries. The difference is the triangular profile for IBM and a pentagonal profile for ISP, because these are two different patented technologies. Then there is a patent technology on retrograde germanium profile at the collector to improve the breakdown process. That is again IBM patented technology. And with the retrograde, they put antimony spike in the base. That's again IBM patented technology. The SIGE transistors can go up to 12 volts. While silicon transistors, they break down at around 3 volts or 3 or 4 volts. So IBM has process which is like 4 volts, 5 volts, or for PA, they have a process which can go up to 10 volts or 12 volts. This is because they are doing some kind of semiconductor physics in the channel and the collector base junction for the breakdown. So you need to know the process to be a circuit designer. So I cannot